Welcome to the second installment of HPLC practicals. In the first practical, we use simulation software to understand how elution parameters affected separation. Parameters such as solvent composition, flow rate, and type have a significant effect on peak retention time and resolution. In today's prac, we'll look at the instrumentation in the lab and use it to collect real data. Here is the familiar screen from the simulation software. Let's use it to understand the instrumentation. HPLC relies upon solvents which are degassed, mixed and pumped at high pressure through the system. Typically a pressure of 200 bar is used. In some cases this can reach 1200 bar. The solvent system is easily identified in the instrumentation. The degasser, mixer and pump are a little bit harder to identify, but this system is capable of degassing and mixing up to 4 solvents in any ratio. Once mixed, the solvents are pumped at high pressure throughout the system towards the column. HPLC requires a sample to be injected into the solvent stream. To do this, a 2-position valve is used. One position allows the loading of the sample loop while allowing solvent to bypass directly onto the column. The other position, as depicted here, allows the sample loop to become part of the solvent flow path through to the column. The real heart of HPLC is the column where the separation of analytes occurs. A real column is shown on the bottom of the image while a diagram is shown on the top. Essentially, a column is a metal cylinder tube through which a solvent can flow. Typically there is 2 columns, a guard column, which is a short column which protects the expensive analytical column from damage. If we have a close look inside these columns, we can see silica particles, SiO2, that is silicon, oxygen, silicon repeated in a 3-dimensional lattice. On the surface of these particles, silanes are grafted. In this practical, the column is C18, meaning that dimethyl octadecyl silane is grafted to the surface. These 18 aliphatic carbon atoms make the particles nonpolar. These particles are tightly packed in the column to ensure they have a very good interaction with the analytes and the solvent. In the case of reverse phase HPLC, a polar solvent, such as a mixture of methanol and water, flows through the column between the particles. Analytes such as 2,5-xenotol and phenotol interact with both the stationary phase and the mobile phase. A polar molecule such as 2,5-xenotol, shown in the top of the frame, dissolves readily in the polar solvent and does not interact very long with the nonpolar stationary phase. A less polar molecule such as phenotol interacts with the stationary phase more, so it takes longer for it to elute from the column. The last parts in the HPL system are the detector, computer and waste systems. The detectors are commonly based on UV-vis systems which consist of a light source passed through a flow cell, a polychromator and a diode array detector. The diode array detector allows a collection of the entire spectrum at once and typically operates at many thousand times a second. An operator can then use the computer system to set up a run. As the columns are expensive and are easily damaged by rapid changes in solvent composition, typically the solvent composition is changed over the course of 15 minutes. The column would then need to stabilize for a further 10 to 15 minutes before the sample is injected. This is the main reason why HPLC1 used simulation software to record the data. In this prac, we're going to use the real instrumentation to generate the data. You can find the chromatographs for the different solvent compositions and flow rates on the Blackboard site. Undertake the data analysis for these chromatographs according to the practical manual to determine the parameters required to answer the questions in the manual. Please remember that this is a full report requiring an introduction, aims, procedure, results discussion and conclusion.